Okay, so I guess everybody here knows me. I'm Amália. I did most of the exercises that we were given, but I will start off by saying that I started off this school knowing basically nothing about seizures or epilepsy, and a little bit, a tiny bit about active matter. So I implemented everything, but I have a lot to study to really fully understand what I implemented, but I will show you in any case. So, the first thing that Ulrike gave us to do was the Fitzhugh-Nagumo model. So it's usually used to describe a neuron, for example. And she gave us these equations here to implement. And when I started implementing that, I went through a big learning curve. But basically what happened is that these equations are not the exact best to find the behavior that Ulrike was asking us to find. So I talked to her a lot, but I managed to understand, calculate, and plot the null lines. So here they are. This is the obvious fixed point, and this is with these equations. So this is a stable fixed point. And then you have some imaginary solution here that's not really important right now. And when we started implementing this here, what we saw is that the null lines, since they were in the previous slide, you can see, they meet at 0, 0. What happened is that since she wanted us to start with x and y at 0, you had a stable solution and it never updated. Otherwise, because we don't have anything else here, you never get the two excitable excitations that she wanted us to see. So this is basically what you got if you shifted the null lines a little bit up, and you couldn't get much further than here. If you search online, you'll see that this continues on and on and on. But this was after a few hours of conversation with Ulrike, so this is what I did for this exercise. And then we added those parameters to be able to shift these lines up. And yeah, this is updating the A parameter that you see here. It updates linearly, and then it turns into a constant after some time. Yes, the blue is the trajectory. This is the phase space. So what you would have if the system was able to do what you wanted us to see, which is a burst with 2 or more maxima, is that this would have sort of, it starts here, goes here, and then it sort of moves up because I'm shifting the null lines up with these 2 parameters. Yes, so that's the first exercise. The second exercise is the modified Hodgkin-Huxley neuron model. We had to read this article by Ulrike that she published about 20 years ago, and that's important because of what I will say in a second. But basically, we had to implement it and try to plot a bifurcation diagram such as this. And what happened was that I could not do it. So what happened was, since Ulrike had published this about 20 years ago, she couldn't remember some of the initial conditions and some of the parameters that were not in the article. So this was an issue I found, that some of the parameters you needed to implement this model were not in the article. So I have the code. I revised it about 3 times. I've read the model section in the article about 5 times. Ulrike revised my code, compared it to the model section, so it seems all right, but there's probably something that they didn't detail in the paper. So if anybody is ever interested in either implementing this or taking a look, I can send my code and we can chat. Yes. And so I move on to Carmen's exercises, and I'll start with the bees, which I guess you know a lot about from David's presentation just a second ago, so I won't go into the model so much. But yeah, what I got is similar. So with a smaller lambda, what you get is always the undecided B's as a majority winning. And then after a while, when you change the lambda, you see that one of the locations that the B's are trying to choose between goes to 0, and they decide on a location, and the undecided are a minority. And you see a very similar type of emergence of criticality, which is also a word I learned. So Carmen's other exercise was the VICSEC model. So I also was not so familiar with this model, but it's how flocking occurs in animals. It's to model that. And yes, this is my implementation. As you can see, they're not, though the parameters are 1 for the radius, they have a lot of noise, so that makes it so they don't flock as much. Here's a graph that is quite similar to Carmen's in the sense that you see this jump here that indicates a jump in the, I guess, it's magnitude of velocity or something like that. And yeah, and when you compare these two, this is with less noise, you see that it's a lot more ordered. So this is the VICSEC model. Also, if anybody wants the code, I can send it to you. I guess it's nothing very new or surprising. I just implemented the exercise. Yes. No. But I want to. Yes. We did talk about trying to implement a power law, but I didn't do it. In the velocity. Yes. And so the last few exercises from Fernando. The first were just properties of active particles. The first exercise was very nice to me because it's what I was the most familiar with, which is, the MSD, since I work with the paramecia. And I implemented it, and it looks quite nice. So here you have a very usual trajectory of an active particle, in the sense that it starts ballistic and it ends up diffusive after a while. And this system is enough to see that. But for the chiral particles, you need a little bit of a larger system. But you see that they also end up with a diffusive movement pattern. So that was it. The second exercise, I just finished implementing it now, so it's not very nice looking. But basically, what you have here is also the systems of equations, and you do a change in variables. So we're looking at spins. And what I computed was the polar order parameter first with dx equals to 0, and then we see the temporal changes in d theta, and then dx larger than 0. So this is what you get, and yeah, this is correct from what I have spoken with Fernando, but it's probably the exercises that I need to study the most, not only because they're the most recent, but it's because they have the most to do with my research. So I guess this is just, if anybody was interested in any of the exercises that we got, here are sort of the answers, and I can send all the codes that I did to anybody that's also interested or trying to implement it. Yes, so I used Python, yes, because it's the most intuitive for me, but otherwise, if I had more time, I would have probably used C, because these are taking a while, and it's annoying, no? Yes. No, I used SciPy.